we completed isothermal process. Now we'll move on to what is adiabatic process and the conditions required for the adiabatic process. Right, boys? Now in an adiabatic process, see, keep this in mind. There are two thermodynamic processes happening, boys. Right? One is, right? I think you have learned about isobaric, isochoric, all those things you have learned, right?
Yes, ma'am. We learned that in chemistry.
So yeah, fine. In thermodynamic process, under physics, you're going to learn basically isothermal and what we call it as adiabatic. And once here, whether you know what we call it as Carnot's heat engine. This is an ideal heat engine. Carnot's heat engine. It's a very important application. If you want to learn all about your heat engines, you have to learn about Carnot's heat engine. It's an ideal heat engine. Why we call it as ideal heat engine is there will be no loss of heat energy. All heat energy will be converted to work. This is what that actually doesn't happen. This is an ideal heat engine. This is the basic heat engine which you can study, hypothetical engine. If you want to study about all your heat engine, how energy supplied is converted to work. Yes or no? How is your automobiles work? The basic working is that the gasoline or the petrol or the diesel are being ignited. So where under the ignition, it becomes a it's a highly exothermic process, right? Now these from liquid state, right? Your fuel will be converted to vapor state, where they are capable of doing work. You can see all the wheels. Okay. The wheels are being attached to the.
Harish, your mic.
Harish, your mic.
Harish, your mic.
Harish.
எனக்கு இங்க நடத்தணும் அது பேர் என்ன அல்சிப் நான் சைக்கிள்ல போக முடியும் அவ்வளவு தூரம் ஏறப்ப
மேம்
அங்க 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 ஒரு இருக்குல
He's wearing. I don't think he's wearing.
Might mute say.
Ma'am, you can mute him, ma'am.
Ma'am, I don't think Harish is wearing his headphones, ma'am. He can't hear you.
Okay, fine. What I have to. So Carnot heat engine is the ideal hypothetical heat engine where whatever heat energy you are supplying, that will be and keep this in mind, boys. The cylinder piston arrangement, if you have gaseous substance included, that becomes a heat engine. It is used in mechanics of your the motion of your wheels. Later on, we study. But in case of hydraulics, it will be filled with brake fluid. All these are coming under hydrodynamics. For thermodynamics, the working substance is basically, even if it is in the liquid state, that is why diesels or petrol, you use your carburetor, the spark plug. The moment you switch on your, I think so now, spark plug comes the moment you just switch on the car. Is that so, boys? Previously, we used to have a spark plug, olden days. Now, the moment you switch on, the carburetor works.
Yes, ma'am.
I'm asking now.
Yes, ma'am.
Okay, where all your these diesel products will be converted to, it will be in a vapor state, it will be pressurized and it will undergo, boys listen, it will undergo both isothermal and adiabatic process. Isothermal expansion, isothermal compression, adiabatic expression, adiabatic compression. The entire gaseous substance will undergo two isothermal process, isothermal compression, isothermal, because the compression of the gaseous substance under constant temperature, expansion under constant temperature, same way, adiabatic expansion, adiabatic compression. So when such things are going to happen, this is called one complete cycle. So these petro products in a highly vaporized state will be made to undergo isothermal compression, isothermal compression, adiabatic compression, isothermal expansion, adiabatic expansion. We call this as a complete cycle. So once it undergoes, during all this process, whatever heat energy you are supplying, that will be converted to work. Anyway, this has been deleted from your syllabus, this Carnot's heat engine. So what you have to basically know is what is an adiabatic process. Adiabatic process is one in which pressure and volume both are thermodynamic variables. Even the temperature of the system are going to change. The reason is there will be no amount of heat energy can enter into the system nor escape out of the system. That's what we said. Suppose the gases are made to allow to expand, then naturally the temperature comes down. Balance the temperature, to keep the temperature constant, the working substance has to absorb heat energy from the surrounding. That cannot happen because heat energy cannot be absorbed from the surrounding because your walls of the cylinder will be insulated. In the previous case, isothermal case, the walls of the container will be perfectly conducting to the surrounding. Have you felt this? I don't know how many of you. If you stand very near your refrigerator, at the rear end of your refrigerator, say near the compressor part, you know where the compressor happens to be. Is a compressor on top or compressor at the bottom part of your refrigerator? At the back.
Top.
Bottom.
You have that one metallic plate shielding it. Your compressor will be at the bottom, right? Spiral tubings are also there, but spiral tubings can come up. Now, do you feel heat energy being evolved?
Yes, ma'am.
Yes, because these working substance, right, they undergo adiabatic expansion suddenly. Heat energy will be transferred to the, it gives away heat energy to the surrounding, but it doesn't take the heat energy from the surrounding. So when heat energy is liberated to the surrounding, you feel hot. But when heat energy is not absorbed by the system, then the temperature of the system keeps on decreasing. So adiabatic process is one in which the pressure, volume, and the temperature of the system. Here we say the temperature of the system is particularly the gaseous substance which is used as a working substance. Now it is not going to change, but there is a change. Why? The reason is that heat cannot escape nor enter into the system. So now for this, what should be the condition? The walls of the container must be perfectly insulated to the surroundings. And second one, this process of adiabatic compression or adiabatic expansion, because your compressor is going to compress the air. Suppose if I am taking air as your working material in cooling system, your compressor will compress air, and then the compressed air is allowed to undergo sudden expansion in the spiral tubing. That is why when air is made to pass through a spiral tubings, it undergoes expansion, and that expansion is so rapid that to maintain the temperature cannot absorb the heat energy from the surrounding. So that is the reason adiabatic process is a sudden process. Clear, boys? So now we'll go for work done in an adiabatic process. Was the same procedure as what we have followed in work done in an isothermal process.
Ma'am.
So you are considering is
Ma'am, is this the last derivation?
yes, this is the last for this chapter finished. So
Okay.
work done in an boys. Work done in an adiabatic process, same way you are considering n mole of ideal gas contained in a cylinder. Fine. Contained in a cylinder having conducting walls. Sorry, boys, I need to change this. So it should be non-conducting. Conducting walls only in the case of the previous case, not in this case. Non-conducting walls and provided with frictionless and movable piston. Let P be the pressure of the gas, right? Because then work done by the gas when the piston moves up. So till this, it's the same. So you're calculating what is the work done. You are supplying heat energy to the working substance. So then this gas undergoes expansion. So as it undergoes expansion, it does a work in pushing the piston upward. So the displacement of your piston is dx. So the work done by the gas when the piston moves up, AW is equal to PdV. Now in this case, only thing is that I have to replace your pressure in terms of the gas equation. It was
Ma'am,
at least yes. What
how are you
happens?
supplying heat if it's like non-conducting?
Non-conducting in that case, boys, the bottom surface can be conducting, the side, right? The walls are non-conducting.
Okay, ma'am. Okay.
Because if you want to understand this process completely, right, you have to go for Carnot cycle, you have to go for indicator diagrams. All these things have been deleted as per the CBSE syllabus, boys. It's too vast. It's vast. Thermodynamics is vast, but whatever the board has specified, we are doing only those things. So the base of the cylinder will be conducting, but the walls of the cylinder will be non-conducting. Only that.
All right, ma'am.
But still, if you remove your heat energy, it can absorb heat energy from the. There are two things what we call it as sink time provides after your examination. Let us see, sink and soaks. These are all the terminologies involved. Since we are not started with anything regarding this, it will take more than 3 periods to explain what is a sink, what is a source, all those process. It's going to be out of syllabus. So I just for right now, you people consider the walls are conducting, the base is, walls are not conducting, the base is conducting. Only that much is enough right now for you. So work done by the working substance when the piston moves up to a distance boys, have you learned about PV is equal to RT, right? This is for an isothermal process. PV to the power of gamma is equal to RT. Have you learned about this? Chemistry, you make this small correction of gamma.
No, ma'am.
You haven't, because it involves specific heat capacities. So that's what I'm asking you. Have you done such things? Right? In anyways, boys, because it's a huge derivation that's right now not required for you. For isothermal process, you consider PV is equal to RT. For adiabatic process, PB raised to the power of gamma. Now, what is gamma? It is a ratio of the specific heat capacity of the working substance at constant pressure to the specific heat capacity of the substance at constant volume. What do you mean by specific heat capacity? What is meant by specific heat capacity?
Ma'am, it's like the amount of heat that needs to be supplied to raise it by 1 degree
Correct.
of temperature.
So yeah, the amount of heat energy required to raise the heat energy of a substance, 1 kilogram of a substance to 1 degree centigrade. Yes?
Ma'am, can you show the previous?
Boys, just to make a note, it's a non-conducting walls, because otherwise it will become. So I'm just right. So now we'll start as what we do, integral calculus. Okay, boys. For adiabatic process, look at the gas equation. It changes to PV raised to the power of gamma is equal to RT. Let me put RT as some constant, because Rydberg constant as well. Sorry. R is universal gas constant. Sorry, boss. Rydberg constant comes in electromagnetic waves. Same notations we do use. You know that R is universal gas constant, T is the temperature. Just we'll put R in RT as K, otherwise not necessary to be put as K, we'll keep it as some value K. Gamma is equal to Cp by Cv. Now what is the value of P now? P becomes equal to RT by V to the power of gamma. So make this as equation 1. Your previous equation dW was equal to, from equation 1, dW was equal to P dV. So dW I have to substitute for P. So it is RT by V raised to the power of gamma dV. How will I write this? RT I can substitute as RT I can substitute as K, correct? And now let us see how I can express V to the power of gamma. So sorry, dW becomes equal to RT into gamma V to the power of gamma minus 1 into dV. Sorry, minus gamma. Sorry, minus gamma. Denominator V to the power of gamma in the denominator goes as V to the power of minus gamma to the numerator. Is that fine, boys?
Yes, ma'am.
What is V? Okay. Now you find total work done. Total work done by the working substance, so that the volume changes from, or so that system changes from state P1 V1 from state. You know that the state of a thermodynamic system can be represented by what? The state of a thermodynamic system can be represented by what?
It's state function.
Okay, what are the state functions you have learned, boys? What are the state functions you have learned? The state of a thermodynamic system can be represented by, okay, you are in chemistry, you are stating it as state function. We state it as thermodynamic variables. What are the state functions? What are the state functions? 11B. Pressure is a state function, is that so?
It is.
Temperature is a state function, volume is a state function. We call it as thermodynamic variable because they keep varying. So now what will be the total work done by the gas so that the system changes from an initial state P1 V1, because a state of a system can, here system means it's the gaseous substance. The state of the system can be represented in terms of pressure and volume, right? And even for that matter, temperature, right? Because your temperature is changing from P1, V1, T1 to P2, V2, T2. Because here the temperature also changes. So now, what is the total work done? W will be equal to, we'll go for the volume change, V1 to V2, dW. You know how to evaluate this integral? Boys, you know how to evaluate this integral? No.
Ma'am, what about the constants?
Like you have to substitute the dW.
Yeah, we'll. So I'll just, instead of I'll just move for only assumptions what we make, sorry boys, only assumption what we make is that, see, the work is done. The dW is a very small amount of work. dW is a very small amount of work, so that the displacement is dx. During this displacement, we'll just consider the temperature to be a constant. That's it. Throughout the adiabatic process, the adiabatic process is that when the volume changes from V1 to V2. That is the entire process. The volume changes from V1, or the system changes from the state V1 to another state where the volume is V2. You have to find what is the total work done by the gas in moving the piston in the upward direction so that it changes from a state which is specified by pressure, volume and temperature to another state where the pressure is P2, volume is V2 and temperature is T2. This is the total work done. What is dW? dW is nothing but the work done by the gas in moving the piston to a very small distance dx so that the gas undergoes a very small change in volume. Only thing is that during this process, we consider the temperature remains a constant. Please understand, during this process of a very small, almost the temperature remains a constant. That is what we need to consider. So, right. Okay, now you substitute, boys. Shall I go for the next slide? Boys, any doubts, any questions being asked? Anyway, physics is tough for you. If I'm asking a question in mathematics, you're not answering. Any question in chemistry also, you are not answering. Shall I go for the next slide? 1 second, sir.
Yes, ma'am.
Oh, okay, sir. I'll okay, sir. Fine. So can we evaluate that W is equal to K, I'm taking it outside, V1 to V2. Is it V to the power of minus gamma? Now look at the identity. X to the power of n will be equal to x to the power of n plus 1 by n plus 1. Yes or no? Boys, when you're evaluating
Yes,
the
ma'am.
integral x to the power of n. Now here, if I'm just putting it so that it's easy for you to understand, x to the power of, say, minus gamma, then how should I write this? So it should be dx over here. How will I write? Sorry, this comes to be x to the power of minus gamma plus 1 by minus gamma plus 1. Can you understand here? Gamma and n are the same. Same way. Are you clear?
Yes, ma'am.
Should I repeat, boys? Anyone who is finding it difficult, should I repeat the identity because you have not done your integration in mathematics? Should I redo the one which I am doing on the right column? 11b, if S means S. At least, can you?
Yes, ma'am. Yeah, if you could do it again, ma'am, please.
Okay.
Yes, ma'am.
Yes, sir. Okay, sir. Boys, I have an important work meeting. So just you carry on with your assignment. What is being given, boys? Just complete. Will you be able to complete the assignment? I'll continue this in the next class because I have to.
Yes, ma'am.
Meeting right now, department meeting. Just you continue. Thank you, boys.
Thank you, ma'am.
Thank you.
Thank you. Thank you.
Thank you, ma'am.